the planning of protection for this alternative, which is the transmission with a little bit more than half wavelength. The overall goal was to assess the behavior of the transmission line in half wavelength under the condition of defects, and the specific goal is to identify the possible critical regions for each defect assessed, both the single-phase and three-phased ones throughout the line. So the AC link is formed with 500 kV lines with similar characteristic as it was presented before, forming 2,600 kilometers, which would be well adjusted for the transmission in half wavelength and 60 Hertz. We are going to present the behavior of the link during the energization maneuver under defect. So for that, we are going to show what was the behavior of the link without the defect, just so we have a reference. And after that, the results considering the occurrence of faults, both single-phase and three-phase applied throughout the line. So with this strategy, it was possible to identify the most critical regions for each type of defect. The simulations were conducted both using ATP as well as PSCAD. The line has already been presented. It's the interconnection between the north-south trunk 1 and 2 and part of the northeast-southeast trunk. The energization of the line was conducted through the closing in the circuit breaker in Serra da Mesa. The intermediate circuit breakers would be interlocked, and the circuit breaker in Bom Jesus da Lapa would be open. The maneuver was simulated considering the poles on the circuit breaker closing at the same moment, the maximum for one phase, in this case, in the maximum voltage for phase A. The surge arresters existing in the lines were considered in the simulation, so they were kept during the simulation for this test, with the purpose would be to redo what would happen with the surge arresters allocated in the lines. We tried not to use any mitigation procedures for overvoltages, so we could really check where would be the most critical regions for each type of defect. So this would be the voltage profile for the energized line without defects and with the surge arresters in the line. So without defect, here I have the profile in regime, and in red would be the maximum transient voltages for the energization maneuver without defect. I'm presenting here some results of the energization without defect, so just so we have a reference point. For this case, the voltage in the circuit breaker located in Serra da Mesa, this is the transient part that takes about 100 milliseconds, and from then on it is in regime. This would be the voltage in the middle of the line, or close to the middle of the line, in the substation of Colinas 2, and the 1,300 kilometers. This is the transient in the higher voltages would be below half of the nominal voltage, and the voltage in regime would be very low, about 30 kilovolts. And the voltage at the end of the line and the receiving end the terminal. And Bom Jesus da Lapa, in regime, we have 1 PU. The faults were simulated considering for the single phase or 3-phase faults applied throughout the line and considering a fault resistance of 20 ohms. The faults were applied in several points so we could determine the critical points for each type of defect simulated. We considered the fault at the moment of the closing of the circuit breaker, a pre-existing fault, and the maneuver in the circuit breaker 100 milliseconds after energization, opening the line 100 milliseconds after it was energized. The total amount of time lasted 500 milliseconds with an integration pace of 50 microseconds. Simulations were conducted without the representation of the coupling effect between the north-south 1 and 2 trunks, and we did not consider the corona effect in the lines because the corona effect would decrease the overvoltage, and our purpose was to verify the maximum voltages that could happen as a result of the faults. So this is the single line diagram for the study of this fault with a single generating unit in Serra da Mesa, the circuit breaker closing the 3 phases at the same moment, and the maximum voltage for phase A. The surge arresters were kept in the line, and we applied the fault throughout the line to verify where the most critical points would be located. So some results we obtained. The voltage in the emission terminal with the fault applied in Serra da Mesa 1. So this shows the same voltage profile in the sun's phase with the behavior without fault, however, presenting overvoltages. This would be the fault applied in Colinas 2, which is located approximately in the middle of the line. We continue with the same format of the voltage without a fault, however, with the presence of the overvoltages. And this would be the terminal fault in Bom Jesus da Lapa, in the receiver terminal, where this would be the most critical region for the single-phase fault, and in reality, the critical region for the single-phase fault starts in group 2, approximately from this point on to the end of the line. So for the applied fault on this point, in this region, we have higher overvoltages. And in this case, it is presenting a maximum overvoltage below 2 PU because it is being limited by the surge arresters which are present in the line. This would be the maximum currents in the circuit breaker in Serra da Mesa. So the current seen from the circuit breaker, it is maximum for the fault point, the terminal near the circuit breaker. As the fault is dislocated throughout the line, the current decreases, and when we reach about half the line, before the Miracema 2 substation, it begins to rise again because it becomes closer of the resonance point of the line. So currents begin to rise from this point on. This would be the current in the transformer that was also monitored. It starts very high for the faults near the terminal, and it goes down as the fault moves in the line. And finally, this graph represents the fault monitored, the fault current. So it starts very high. As the fault moves in the line, the maximum current goes down until they reach about half the line, and then they go up again because it becomes closer to the resonance point in the line. And then it goes down again. So you can better visualize what the most critical regions would be for a single phase fault. I have included here the graphs from the surge arresters that performed or had some kind of performance during the applied faults. So in the beginning of the line, the surge arresters that worked was the one located in Miracema 1, located on the 511 kilometers in the line, where it act around for the fault around Imperatriz with an absorbed energy. The absorbed energy in the surge arrestor was not very high, and it also worked for the faults applied from Serra da Mesa 2 until the end terminal in Bom Jesus da Lapa. So near the substation of Bom Jesus das Éguas, but reaching almost the limit for energy absorption of the device. Talking about the surge arresters. In Colinas 2, a substation near Miracema, its surge arresters were also working for the faults applied throughout the line. So for the faults near Imperatriz 1, the surge arrestor had some work, and a largest amount of work for the faults applied from Serra da Mesa on, following a similar behavior to the surge arresters located in Miracema 1. These are substations which are very close to each other. So we can see a critical region being formed for a single phase fault near the end of the line. The other two surge arresters who were more demanded were the surge arrestor located in Rio das Éguas at the end of the line, and surge arresters located in Bom Jesus da Lapa. Both working in the same region in regards to the faults that were applied, so near Imperatriz, and for the faults applied in the end of the line from Gurupi 2 on. And the surge arresters in Bom Jesus at the end terminal, they were the most demanded ones with the applied faults here. So on these surge arresters, the absorbed energy was higher or above the device capacity. So this region from Gurupi 2 until Bom Jesus da Lapa, this would be the most critical region for a single phase fault in the line. So we visualized the behavior of the link without a defect and with a single phase fault throughout the trunk of the link. As we had seen before, the energization without effect does not present severe overvoltages, and the energization with a single phase fault presents critical regions after kilometer 2000 at the end of the line, close to the receiving terminal. So only the faults located in this region generated over voltages that were higher in the line, and consequently higher fault currents. So the current values in the circuit breakers were larger for terminal faults close to the circuit breaker, and this goes down as the current fault goes down, as the current or as the fault dislocates throughout the line, up until the medium point where it rises again in the critical region, which would be near the resonance point of the line. The surge arresters, as we have seen, they were not required, with the exception of the ones located in the critical points, which were very well defined. So for the faults located around Imperatriz, and for the faults located in the end of the line from Gurupi to until the end of the line. These were the two locations where the surge arresters had a considerable amount of energy. The defect was capped for 100 milliseconds. And in this case, for these simulations, the performance of protection was not considered. Here we just wanted to verify the maximum overvoltages that might happen. The three-phase faults were simulated under the same conditions as the single-phase ones. The three-phase faults were also applied throughout the line, considering as a fault resistance of 20 ohms. The line was also a non-load line. Both for a single-phase and three-phase line, the line was always a non-load line. In the same way as the single-phase one, the three-phase fault was applied in several points so we could map the line to find the most critical regions. Simulations were also conducted with ATP and PSCAD. So here I'm showing the graphs for the voltages as the fault moves throughout the line. So starting here, and the terminal fault does not cause an overvoltage. Here the results were implemented or simulated with ATP and PSCAD. ATP is the blue line, and PSCAD is represented in the red line. ATP is showing more conservative results in this case. So as the point of fault moves in the line for the three-phase fault, the voltages the backward to the fault point, they become higher. So Gurupi, Miracema 1, so the voltages, they start to become higher upstream up until the faults in Colinas 1. We still do not have over voltages in the beginning at Serra da Mesa. So the fault applied in Imperatriz also does not present over voltage value which is higher than 1 pu. From Colinas 2 on, we start to see over voltages from the three-phase fault applied. But the critical point starts from this monitoring point located in Miracema 2. So from this point on, downstream, we start to have a very high overvoltage, and its value is only being limited by the surge arresters located on the substations downstream to the fault point. So in the following substation in Gurupi, which is about in the average point of the most critical region, the over voltages downstreams are going to be limited by the surge arresters working in Imperatriz, Colinas 1 and Miracema 1, and also in Serra da Mesa, up until the fault located in Serra da Mesa, where we have the surge arresters working. From this point on, the overvoltages go down, and then we would not have the surge arresters working. And the terminal fault located in Bom Jesus, basically we do not have a very considered considerable overvoltages in comparison to the values observed in the critical region. So looking at the overvoltages from the circuit breaker located in Serra da Mesa, we can see the most critical region for the three-phase fault applied. So it's from this region of Miracema 2 up until Serra da Mesa 2. In this region, we have the most critical region where faults in these points will cause overvoltages and the surge arresters to be triggered. In the substations of Gurupi, Miracema 1 and Colinas 1, including Serra da Mesa as well. The fault currents seen by the circuit breaker in Serra da Mesa, both with ATP and PSCAD. It starts very high, and in the terminal fault located, in terminal fault located in Serra da Mesa, it goes down in magnitude until it becomes closer to the resonance region, where it starts to go up again. Here we have some graphs I included to present the behavior of the voltage for a fault located in the average point of the critical region, which is Gurupi. The voltages in Serra da Mesa are limited by the work of the surge arresters. And the same way, the voltages in the substation of Gurupi, they are also limited by the surge arresters. Just to visualize the behavior of the surge arresters, here you can see the absorbed energy on each of them. On the surge arresters in Serra da Mesa, where the circuit breaker is located, and here this work of the surge arresters in Gurupi, Miracema, and Colinas, so becoming closer to the limit value of the surge arresters' supportability. This would be the fault current for a fault occurring in Gurupi 2, as seen from the circuit breaker. In this case, this current is also being limited by the surge arresters. In the case of the lack of a surge arrestor, this could be much higher in terms of the fault current. The voltages in the circuit breaker for faults located up until Imperatriz will always be lower than the nominal voltage of the line. The region, we have observed that the critical region for three-phase faults is located between the substations of Miracema 2 and Serra da Mesa 2, which comprises 65 to 85% of the length of the link. We will have the worst cases for three-phase faults, and these values are only limited by the surge arresters' presence on the substations, including the substation of Serra da Mesa. With that, we see that in the surroundings of the substation of Gurupi, we have the worst cases with posing risks at the surge arresters, the forward located downstream, about 1/4 of the wavelength. So we're talking about the surge arresters located in Gurupi, Miracema, and Colinas. So for three-phase faults in this region, besides the removal of the fault in an lower time than 100 milliseconds, it would be necessary another protective measure for the line. One option would be the use of the reduction of isolator chains, which will be covered during this seminar tomorrow. I'm just going to conclude now. I was going to summarize. Just so summarizing, for single-phase faults, they are basically, well, they have the most critical location from the substation of Serra da Mesa 2 until Bom Jesus. So we're talking about large region a very specific region. It's a very specific region near the end terminal. The currents were not higher due to the work of the presence of the surge arresters. So we saw the severity of the fault related to the absorbed energy of the surge arresters located downstream. And the surge arresters were requested only for faults located in very specific points from the substation of Gurupi 2 until the end of the line. This would be the most critical region for the single-phase fault. So the occurrence of defects throughout the line can produce different results from the ones found in short lines. And this was observed specifically due to the occurrence or the work of the surge arresters located further away from the fault point. Possible solutions for a single-phase fault would be the use of a fast protection or the use of surge arresters with a higher capacity of energy absorption. And for three-phase faults, just quickly concluding, both from the point of view of overvoltages as from the dissipated energies in the surge arresters, the worst cases happen in a very defined region located between Miracema 2 and Serra da Mesa 2, focused on the substation of Gurupi 2. The overvoltages were limited by the work of the surge arresters and limited at about 2 pu, but this limitation happened due to the surge arresters located in the line. Dissipated energy on the surge arresters is very high, being close to the limit values. So in the substations of Miracema 1, Colinas 1, and Serra da Mesa 1, in the beginning of the line, were the most demanded points for three-phase faults. The values obtained are always higher the current value in regime when we're monitoring the current. This would be the capacitive current of the line. In this case, for the test, the faults could be identified using a subcurrent relay. So basically, this was the results we obtained and wanted to share with you. Thank you very much. Thank you very much, Marcos, for your excellent presentation. We are going to open for questions, and I'm sure there are going to be some questions about surge arresters from Balestro. I'm Camilo Lima from Potens. Professor, in your presentation, for three-phase faults in Serra da Mesa, the ATP results were different from the PSCAD results, especially in the currents with a difference of 1 kiloampere between one tool and the other. Can we attribute these difference to the model of the machine used and ATP or PSCAD, or do you have another reason for that? ATP uses the line represented by distributed parameters, and on PSCAD we use the representation that takes into consideration the variation of the parameters with the frequency. So this also influences the results. the model of the line. So your explanation would be the influence of the frequency on the parameters. And this is on the PSCAD representation. And ATP did not include, although it could, considering the Marti routine, but this was not done. And the machine model is exactly the same. I don't know if Cristina has something to add. The machine is represented by an ideal source behind an impedance. The representation of the machine is the same, the conventional model for transients. We are not representing the machine in this study. So the source through an impedance, then you have the transformer. The difference between the models is how the line was modeled. I'm sorry, I had imagined that the machine had something to do. Not in this case. Not in this case. Only tomorrow. Only tomorrow. Then we're going to have a dynamic analysis. But for transients, we are only using one source. Just to summarize it. So the model of the line created this difference. That's it. Yes, the model of the line, because we do not work with the Marti model. The Marti model for dependence of frequency in the parameters does not work very well. We do not consider it to be suitable. So to represent the frequency, we use the phase model in PSCAD. It gives us a good response. So the difference is only the model of the line. If you did the Marti in the ATP, would you become closer for the PSCAD value? The Marti model can be unstable, so we cannot use it. We do not trust the results. It can be closer, but there can also be some differences in the results. Although we are working with with an ideally transient transposed line. The simulation was done without the presence of the surge arresters in the line? No. The surge arresters were always represented. You have already answered half of my question, because I was going to ask you, since we are trying to simulate a link without the surge arresters in the line, if you had already done the simulation, which would have as a purpose perhaps learning about the overvoltages. But the problem is, since we are studying, when we are preparing for the test, and the surge arresters do not have an impact when the line does not have a defect. And our idea is to conduct the test during a day where we don't have a high probability of rain. But we're talking about 2,600 kilometers, so a single-phase fault can happen. A three-phase fault is very unlikely to happen during the test. It will be a lot of bad luck for it to happen, but not for the single-phase one. So in reality, when we verified the stress of the three-phase fault, it's more just to complement our task list, because we really do not expect for it to happen. After that, of course, the protection needs to be for all types of fault. So that's why we have kept the surge arresters, because during the test they will be there. And for the amount of energy, we know that the overvoltages will be high, really high. This is why the mitigation method we are proposing that is going to be presented on the TRT project tomorrow, because the energy is high. For single phase fault, which would be a more likely phase to happen, could happen at least with a little bit higher probability, we have a problem of the energy of the surge arresters located in the end of the line. The energy is high, but as we're going to see with the protection tomorrow, the conventional protection today is already enough not to allow the overvoltage to become too high. The three-phase fault only happens if there is air crash on top of the line, or if the tower falls down. There are no other alternatives for three-phase fault, okay? Just to heat up the discussion, Cristina, when you think you've had enough, please interrupt me. But regarding the energy absorption, I'm sure you remember the conversation we had on CNPT regarding the inadequability of the varistor models, for example, for ATP, to simulate or really show the capacity for energy absorption in surge arresters. When we put MOV92 in the circuit, it behaves as an ideal surge arrestor. The current is always the same. You can support over almost a million joules. But by the figures I have seen, the three-phase fault would eliminate a lot of surge arresters. They would actually fail. But what happens is, if this was a half wavelength line, the surge arresters would not be there because they will only be in the terminals. And besides the simulation indicating 1.5 pu, before that the arc starts to break. If you do not do anything, the line will leave the resonance condition. But we control this output through our proposal. Exactly that. Put a surge arrestor, it would be better. My name is Osvaldo from CHESF. You mentioned that the representation, I think Maria Cristina also said this, the representation of the parameters of the line, it was a perfectly transposed line. The perfectly transposed line, and of course, as you mentioned, you didn't mention it, but you did not consider mutual parameters, because there is a segment where the line is one direction, so we do not consider the coupling. Only 60 meters between trunks. If it was a short line, imagining 800, 1,000 kilometers of parallel line, this could have an influence. My question would be, would it be favorable or not for these overvoltages? This is my question. Maybe it may be favorable. We cannot imagine it. Perhaps if you have the opportunity. We did not study coupling because the lines are far from each other. The north-south trunks are 60 meters away from each other. So in terms of impact on the overvoltages we are observing, this would not be important. There could be an influence when the line would be on a permanent regime on the minimum voltage area, in the middle of the line, because then we have a 30 kV voltage and there will be a coupling. Perhaps we have to calculate the impact on this. But distorting our half wavelength test line, this would not be important. My name is Roberto from CPEL. Just one question. This elevated energy amounts in the surge arrestor when there was a defect on the phase A, is this elevated only on the phase C? It was the phase where the surge arrestor was requested. So the impression I get, if we did not have the surge arrestors, as both of you have mentioned, the overvoltages would be very high. So occasionally, this single phase fault would become a two-phase fault, because for sure that would be a discharge in the isolator chain on the phase C. Since the overvoltage, I believe the overvoltage would be high. And maybe, disagreeing with Vanderlei, this would become a three-phase fault even if there wasn't a plane crash. Let's forget about the plane. From what we have seen in terms of studies without the surge arresters, we reproduced this case on RTDS using the protection that exists currently. And the protection is extremely fast, because when the fault happens in these critical regions, the current in the beginning of the line is too high. So it's almost like a terminal fault. It's instantaneous. You do not have this amount of energy. We're going to show this tomorrow. I just don't want to show you the end now of the story. But because the protection works so fast, energy in this point does not exist. We're talking about 100 milliseconds, and protection. I don't remember the value exactly. Celso is going to say it, but it's extremely fast. For the relay, it's a terminal fault. It's very fast. If there was a problem with the protection, then yes. But the protection that was there installed on NTDS did not allow for the energy to reach this point.